Everyone is calling the model's context window its memory, but it's not memory because memory is something that you store and then you look it up when you need it. But context window, you resend all of it every turn and you pay for it. Start with what happens every time you hit send. The model isn't sitting there, remember in your conversation, there is no session. So every time you send a message to the model, your app takes all the turns so far and puts them into one big blob of text, which is then sent to the model. Then the model reads that blob, and to produce the next token, to produce the new token, it looks at every other token before it. Okay, not only the important ones, it will look at every token. This mechanism is called attention, and by the way, I have a separate video on it. And this is the most important part for this video. You have to keep this in mind. Okay, let us now try to conceptualize what happens here when you hit send. So we have two main phases over here. The first one is prefill. This is the model reading your input all at once. All the tokens in your input are processed in parallel at once. So this is why, for example, you may have to wait for some time when pasting a big file. And then we have decode phase, which takes the result of the prefill, which loads the result of the prefill phase into memory, and then works with it to start writing tokens. It writes one token at a time, and this is what you see when the model starts streaming tokens onto your screen. Okay, so both decode and prefill phases, they drag a lot of data around, but let's try to understand their difference in terms of the useful work that we get per such whole. So prefill, in order to process your input, it walks the model only once, and then it does a lot of parallel computations, and that's it. So we drag the data out of memory just once, and we do a huge job. So its potential bottleneck becomes the computational power of your GPU chip. So by acquiring a faster chip, we can speed up prefill only. The decode phase, on the other side, loads the model for every token. So if it generates 500 tokens, it will load the model 500 times. So we do these huge holes every time just to do a tiny job. So decode becomes memory dependent. Its potential bottleneck is the memory speed. So by having a faster memory, we can speed up decode only. And prefill can get expensive really fast because, as I said earlier, during the prefill stage, every token looks at every other token. So if we have 4 tokens, that means we are going to need 16 comparisons. If we have 8 tokens, we are going to need 64 comparisons. So we clearly have a quadratic function over here with a time complexity of order n squared. And all this cost, it lives in prefill because decode doesn't pay for it. In decode, we just compare the new token to the cached tokens provided by the prefill. So we don't do these quadratic comparisons every time in decode. Okay, now let me actually show you what I'm talking about. So I have this small Python code which prompts the same local Qwen model with the same question and always gets the same answer. Now, the only thing that changes is that the amount of junk text that I put in front of the question increases every time with each new request. So what we are interested in is to measure and compare the time to first token in seconds. So the first prompt has just 62 tokens and it has no junk text in front of it, in front of the question, and the time to the first token is just 2 seconds. Then I add some filler text in front of the prompt, and now the amount of tokens is almost 9,000. And look how the time to the first token increased. Now it's almost 6 seconds. Then almost 80,000 tokens, and the time is 11 seconds. And then for 25,000 tokens, we have 16 seconds until the first token. And pay attention to the middle two, because it clearly demonstrates us that by doubling the filler text, we more than double the time to the first token. Now, all this computation is not lost on every turn, and in order to generate the next token, the model doesn't have to do all that we have just discussed. Because actually the prefill phase leaves behind its result, which is called the KV cache. Now, I have discussed the QKV triplet in one of the previous videos. I'm not going to go deep on it right now. If you are interested, I will link that video in the description. You can watch it, but what you have to understand is that each token gets a key and a value pair, and that is the KV cache. Okay, but how big does this get really? Let's multiply it out and find out. So we have the key and value vectors. Each vector contains a few hundred numbers. Then each number is a couple of bytes. And we multiply this number of bytes by every layer and by every head that is inside every layer. So in the end, we get real gigabytes sitting in our GPU. And as you can guess, this gets expensive pretty fast. Keep going long enough, and your KV cache is bigger than the model that it's serving. So it's natural to ask, how come that a 1 million token window exists at all? Well, there are three common techniques, tricks you may call them, which are used to achieve this. The first one is called grouped query attention, and its idea is to group some heads around the same key and value pairs instead of each keeping their own. The second approach is to store those numbers at which are in the key and value vectors at lower precision. For example, instead of 60-bit floating point number representation, we can use just an 8-bit to write those numbers. And the third approach is to spill the cold cache, the least recently used cache, to system RAM or even to disk. And of course, all three of these approaches, they cost you something. Okay, so the cache is a good thing, right? Because it allows the model to never start again from scratch, but it has to live somewhere. This is the consequence, and it lives in your VRAM. That's why long context eats it, and that's why the same question costs you more when the chat is long. Okay, but where does the cost actually come from? So here's the thing, one GPU serves many requests at once. But what decides how many requests fit in? The KV cache is what deciding it. So for short contexts, we have shorter caches, and it's okay, the GPU can serve them all. But for long contexts with bigger caches, we have a problem, because you are not just paying for compute. Your long context occupies the GPU, so you end up paying for your share on that GPU. So there is a version of this that you can actually control, and I bet you've heard this a lot. The prompt caching. The provider keeps computed cache for the front of your prompt so that it doesn't redo all that work every time, but it matches from the start only, which means change one character near the top of your prompt and it recomputes the whole thing. In practical terms, how to order your prompt around this idea? It's pretty simple. Put this table stuff, for example, the system prompt, tool definitions, to the top of your prompt. Then goes the semi-stable stuff like documents or examples, which can change but it is unlikely. And then the volatile stuff goes at the bottom of it, like your conversation itself, the new message. The rule is pretty simple. Always append Never exceeds the top. The naming is confused, so don't let me trip you up over here because those are not the same thing. The first difference is that, yes, while they still both keep cache for the key and value vectors, they have completely different lifetimes. Because this one, it lives inside one request only, while the prompt caching, as a concept, as a technique, lives across different requests. This is when the provider just stores this cache for you. Now, the second difference is that one of them is automatic, okay? But for the other one, you can actually design for. Okay, now, so what this changes about how you use it? The first thing to keep in mind is that the whole conversation goes back every turn, and you pay for all of it every turn. And the model's automatic KV cache can't help you with your bill, but prompt caching actually can. That's why you have to put the boring stuff, like the stuff that is less likely to change, at the top of your prompt. And the final piece is that shorter prompts, they actually save you more than it looks like. Okay, that's it. Thank you for watching.